Okay, this video will go over, obviously by the title, function operations and function composition. What we mean by function operations is when we're adding, subtracting, multiplying, or dividing functions. Like if you see f plus g of x, that just means you add the functions together. If you see f minus g of x, that means you just subtract the functions. Likewise, when you see fg of x, that just means you multiply. And you see f over g of x, that means you just divide the functions. Whenever you're dividing the domain of this composite function, f over g, it's just all the x values except for the ones that make the denominator equal to 0. So for example 2, it says let f of x be equal to 8x minus 9 and g of x be equal to the square root of 2x minus 1. Find each function in parts a through d, and part e says find the domain. So for part a, it says f plus g of x. So that would be equal to f of x, which is 8x minus 9 plus square root of 2x minus 1. And you can simplify the, or actually you can't simplify this. So the domain is where the square root, the radical is non-negative, so this 2x minus 1 has to be greater than 0, which means 2x has to be greater than 1, because if you add 1 to both sides, that should be greater than or equal to, so x, we want all the x values greater than 1/2. We can remember the domain for f of x is just all real numbers because it's a linear function. So the domain is the set of all x values such that x must be greater than or equal to 1/2. You could also write it in interval notation. Since it can be equal to 1/2, it'd be from 1/2 to infinity. You'd put a square, you'd put a bracket next to the 1/2 since it can be equal to 1/2. Either way of writing the domain is technically correct. And of course, this part would be rewritten, would be f plus g of x. That part would go right there. For part B, f minus g of x, that's equal to 8x minus 9 minus the square root of 2x minus 1. So the domain's still the same because we cannot have a negative number underneath the square root. So this has to be, the 2x minus 1 must be greater than or equal to 0 because it has to be non-negative. So x must be greater than 1/2 if you remember from earlier, so the domain would be from 1/2 to infinity. Part C, f times g of x, that would be equal to the formula for f, which is 8x minus 9, times the square root of 2x minus 1. So, you could leave it like this, since it's a square root. So, the domain would be equal to, again, you can't have a negative number underneath the square root, so the 2x minus 1 has to be non-negative, so the domain would still be the same, from 1/2 to infinity. And for f divided by g of x, that's equal to the function f, 8x minus 9, divided by the function g, which is square root of 2x minus 1. Now, since you cannot have a negative number underneath the radical, and you cannot have 0 on the bottom, this must be the input must be strictly greater than 0, which means x must be strictly greater than 1/2 if you remember from earlier solving for x. The number that you solve for, it'd still be the same, it's just that instead of it being greater than or equal to, it must now strictly be greater than. Since it's greater than, the interval for the domain would be the same, it's just that since it cannot be equal to 1/2, you do a parentheses now. So the domain would be all the x values greater than 1/2. Okay, so now here's an example where you do the same thing, but like instead of f plus g of x, you'd have f plus g of a certain number, in this case 1. You can start by working out the same way. You can find f plus g of x. If you do f plus g of x, you can just add them together. X squared plus 1 plus 3x plus 5. Add them together, that'd be x squared plus 3x plus 6. So now f plus g of 1, that's equal to, instead of x squared, it'd be 1 squared, plus, instead of 3 times x, it'd be 3 times 1, plus 6. So that'd be 1 squared is just 1, 3 times 1 is 3, plus 6, which means f plus g of 1 in this case would be 10. For part B, it says f minus g of negative 3. You start by doing the exact same thing. You can do f minus g of x, which would be x squared plus 1 minus 3x plus 5. That would be x squared plus 1. Distribute the minus sign, so it would be minus 3x minus 5. So that would be x squared plus 3x. That should be minus 3x. And then positive 1 minus 5 would be minus 4. So f plus g of negative 3. Minus g, I'm sorry. So f minus g of negative 3. It's equal to, instead of x squared, it'd be negative 3 squared. Minus 3 times negative 3 minus 4. Negative 3 squared is 9. Then negative 3 times negative 3 would be plus 9, and then minus 4, which would be positive 14. So for now, f times g of 5. You start by finding out f times g of x. That would be x squared plus 1 times 3x plus 5. Now if you want to FOIL this out, x squared times 3x would be 3x to the third. X squared times 5 would be plus 5x squared. Then positive 1 times 3x would be 3x, and then positive 1 times positive 5 would be plus 5. So now f times g of 5 would be 3 times, instead of x to the third, it'd be 5 to the third plus 5 times 5 squared plus 3 times 5 plus 5. Now 5 to the third is 125 times 3 would be 375 plus, now 5 squared is 25. Multiply that by 5 and that's plus 125 plus 3 times 5 is 15 plus 5. Now 375 plus 125 is 500 plus 15 is 515 plus 5 is 520. So for part D, f over g of 0. Now let's start off by doing f over g of x. That would just be f of x, which is x squared plus 1 over g of x, which I believe is 3x plus 5. Now that cannot be simplified, so we can now do f over g of 0. So that would be 0 squared plus 1, instead of x squared plus 1, instead of 3 times x, it would be 3 times 0 plus 5. 0 squared is 0, plus 1 is 1, 3 times 0 is 0, plus 5 is 5, so the answer would be 1/5. Alright, here's another way to think about it. Say, for example, let me illustrate this with an example. If f of x is equal to 2x minus 1, g of x is equal to 3x plus 2. Now I want you to determine f plus g of 3. Now, the other way, besides just finding out f plus g first, is you could find f of 3 and add it to g of 3. Because remember, f plus g of x, this is why we can just take f of 3 separately, g of 3 separately, and add it together. Because remember, f plus g of x is equal to f of x plus g of x. So technically we could take the value of f separately and the value of g separately and add them together. So in this case, if you plug in 3 into f, you have 2 times 3, which is 6, minus 1, which is 5, plus, and so g of 3. 3 times x, which would be 3 times 3 is 9, plus 2 is 11. So f plus g of 3 in this instance would be 16. Now I show you that pretty simple example to illustrate this a little bit more complex example. Alright, here's the first part of our third example. Use the given representation of functions f and g to evaluate. Let's first start off with f plus g of 4. That's equal to, remember that's equal to f of 4 plus g of 4. So that's equal to, see, f of 4 is 9, because it's right here, and g of 4 is 2. So it'd be 9 plus 2, which is 11. Now f minus g of negative 2. That's equal to f of negative 2 minus g of negative 2. Now if you notice, the domain for g of x does not go past 0, so it's so this function g of x is undefined at x equals negative 2, so f minus g of negative 2 is undefined. So now, f times g of 1. F of 1 is, if you come up here to where x is 1 on the linear equation, notice the y value is 3, and then for g of x, the y value at 1 is strictly 1. So it's 3 times 1, which is 3. Now f over g of 0. Alright, let's start off with f of 0, which is right here. It's 1, because remember, this, where x is 0, that's just the y-axis, because the y-axis goes through where x is 0. So, f of 0 is 1. Now g of 0 is just 0, so you have 1 over 0, and so you can never divide by 0. That would be undefined. Now, remember, whenever you're doing work or taking an exam, it's always best to box your answers in. Next thing we're going to learn about is composition of functions. If f and g are functions, then the composite function is obtained by plugging f of x everywhere there's an x and g. in the domain, set of all numbers x in the domain of f such that their corresponding y values are in the domain of G. So, here's some examples. The 2 goes away, the 4 reduces to 2, so it'd just be 2 over x minus 1. However, keep in mind that if I tell you to find just g of f of x. And that would be your final answer in this case. But I didn't ask you to do that, I asked you to find g of f of negative 3. So you can plug in this negative 3 into x, so just 2 over negative 3 minus 1, which would be 2 over negative 3 minus 1 would be negative 4, so that would reduce to negative 1/2. Alright, so here's another example. Given that f of x equal to the square root of x and g of x is equal to 4x plus 2, find each of the following. Start with part A, f of g of x. Remember that means f of g of x. That just means everywhere there's an x in f, you can replace it with 4x plus 2. So that means instead of the square root of x, it'd be square root of 4x plus 2. Now to figure out the domain, the discriminant, the stuff underneath the radical, has to be non-negative. So 4x plus 2 has to be greater than or equal to 0. So now, if we solve for x, get the 2 on the other side, you have 4x is greater than or equal to negative 2, which means x must be greater than or equal to negative 1/2. So the domain would be the interval of all x values from 1/2 to infinity. And it would be a bracket around the 1/2, since our x value can be equal to 1/2. Now for part B, g of f of x. That's equivalent to g of f of x, which is equal to g times, or g of square root of x. So that means everywhere there's an x and g, you plug in square root of x. So instead of 4 times x, it would be 4 times square root of x plus 2. So now to find the domain, alright, we know with the radical, it has to be non-negative, so the stuff underneath has to be greater than or equal to 0. So the domain, since it has the square root of x in it, it'd just be from 0 to infinity. Again, it'd be a bracket around the 0 since x can be equal to 0. So now, here's another example. Given these two functions, 6 over x minus 3 and 1 over x, find each of the following. First one is f composed with g of x. So f of g of x. Remember, that's equal to f of g of x. And that means everywhere there's an x in f, you plug in the function g, which is 1 over x. So that means, so 6 over x minus 3 would be 6 over 1 over x minus 3. Now, you see how we have a fraction over a fraction being subtracted by something else? We need to get rid of this fraction right here. The 1 over x. The way you do that is multiplying by the denominator, multiply by x. But remember, what you do to one thing, you have to do to everything to keep the function equivalent. So if you multiply by x, those cancel out, so on the bottom you'll just have 1 minus 3 times x, which is 3x, then 6 times x, which is 6x. And so now that we have our fraction simplified, our domain, remember to find the domain, this part here, the denominator, it cannot be equal to 0. Which means negative 3x cannot be equal to negative 1, which means x cannot be equal to 1/3. It can contain any other x value, just not that one, because that would make the denominator equivalent to 0. So the domain would be the set of all x values such that x cannot equal 1/3. And that's a squiggly. That's supposed to be one of those squiggly brackets. So now let's figure out part B, g of f of x. Remember, that's equivalent to g of f of x. So that means everywhere there's an x in g, you just plug in the function f, which I believe was 6 over x minus 3. So that means it'd be 1 over 6 over x minus 3. So if we're dividing by a fraction, you can flip the fraction and multiply. So instead of dividing by 6 over x minus 3, you could multiply by x minus 3 over 6. Since we're multiplying this fraction by 1, that's just equivalent to x minus 3 over 6. And now just so you know, you may recognize this if you split into separate fractions, x over 6 minus 3 over 6. Since we're dividing x by 6, that'd be 1 over 6 times x minus 3 over 6, which is 1/2. You might recognize that as a linear equation. And we know the domain for any linear equation is just the set of all real numbers. So it'd be the set of all numbers from negative infinity to positive infinity.